This is the 18th video on my multivariable calculus. In this video, we're going to talk about double integrals and how we can evaluate them. So in single variable calculus, integral of f of x from a to b evaluates the area underneath the graph of f of x, y equals f of x, from x equals a to x equals b. So this area can be evaluated by integral from a to b of f of x dx. Now, in multivariable calculus, and specifically for functions of two variables, we want to evaluate something similar, but it would be a volume. So the volume of the region underneath the graph of z equals f of xy and above a region r in the xy plane is denoted by the integral of f of xy dA. So if the region in the xy plane is R, and here I'm drawing a rectangle, but it could be any region, then the volume of this solid is going to be the double integral over R of f of xy dA. So f of xy is height and dA is the area. Once you multiply the area by the height and you add it up, you get the total volume. Let's look at a pretty simple example. So the first example we're going to do is, given a triangle in the xy plane, triangle with vertices 0, 0, 0, 0, 1, 0, so this point, and 1, 0, 0, we want to evaluate integral of 1 over this region R. So this is R, and that would be our base, and we want the height to be 1 because the integrand here is going to be the height. So we want to evaluate this integral. So what is the region that we get? The solid that we get has a triangular base, which is the triangle that I have down here. It's a red triangle, and the height is 1. So what is this? This is a prism. So this area, or this volume, is going to be area of the base, so it's area of R, times the height, and height is 1. So the base is a triangle, and base and height of this triangle are 1. So it's 1/2 times 1 times 1, and then times 1 for the height. So the whole thing becomes 1/2. So this double integral is just 1/2. Now, in general, to evaluate double integrals, we need a notion called iterated integrals. So what is an iterated integral? And I will do an example, and then we'll relate the double integrals that we talked about and iterated integrals. So what is an iterated integral? It means we integrate with respect to x, and then we integrate with respect to y, or we integrate with respect to y, and then we integrate with respect to x. So this is what it means. Now, why does that mean something? It's because when you evaluate this double integral, area of the base, this dA, would be dx times dy, which is the same as dy times dx. So what we do is we replace those small pieces of area by dx times dy, and that gives us the entire area of every piece. Okay, let's first do an example, and then we'll do an example on evaluating double integrals using iterated double integral. So this is an iterated double integral in A, and same thing for B. So what we do is we start integrating, but we're gonna have to make sure that the integration is done in terms of the appropriate variable. So this is integral from 0 to 1. Integration of the integrand x plus 2y with respect to x would be x squared over 2 plus 2yx. And then I'll have to plug in different values of x, the limits of integration. But you would have to make sure that you plug in x equals 1 and x equals 2. And then we do dy. So we get integral from 0 to 1 When we plug in 2 for x, we get 4 over 2 plus 4y minus, then we plug in x equals 1, we get 1 half, and then 2y and dy. So that's integral from 0 to 1. 4 over 2, that's 2, plus 4y minus a half minus 2y dy. This would be integral from 0 to 1. We would get 2y from these two plus 3 halves dy. Finally, we integrate with respect to y. We get y squared plus 3 halves y. And then the limits of integration are 0 to 1. Because here I have multiple variables, I always indicate which variable I am substituting. So this would be 1 plus 3 halves minus 0 minus 0 minus 0 plus 0, which is going to be 5 halves. So the answer for the first one is 5 halves. We'll do something similar for the second one, integral. Second integral is integral from -1 to 1. The integrand here is going to be, it is 3x squared plus 2y, but the integration is done with respect to y. So I'll have to take the integral with respect to y. So it is basically like partial differentiation. These are basically like partial integration. So we assume that x is fixed and we differentiate with respect to y. So this would be 3x squared y plus y squared, and the range for y is 0 to x. And we do integration with respect to x next. Okay, so let's plug in the two values of y. We get 3x cubed when we plug in x plus x squared. And then we plug in 0, which would be 0 dx. Next, we're going to integrate this with respect to x. So 3x to the fourth over 4 plus x cubed over 3. And then the limits of integration are -1 to 1. If you plug in 1, we get 3/4 plus 1/3. And when we plug in -1, we get -3/4 minus 3/4, and then minus a third. And this becomes 2/3. So the answer to this iterated integral is 2/3. Now we're going to relate the double integrals and iterated integrals. If the region that we are given is a simple region, so if we have a region that is a rectangle bounded by x equals a, y equals b, x equals a, x equals b, y equals c, and y equals d, if it is bounded by these, we could either say, well, y goes from c to d. So if you look at a fixed x, we will get the limits of y are from here to here, and then x ranges from a to b. So this one gives us the first integral. If we go horizontally for any given y, if you fix y, the range for x is going to be from the left side of this rectangle, which is a, to the right of the rectangle, which is b. And then, of course, y ranges from c to d. So for every y ranging from c to d, the limits of x is between a and b. So these two are the same. This equality is called Fubini's theorem. If you have a region that is vertically simple, which means your region is x is between two constants, so x goes from a to b, so from here to here, and y goes from two functions, so you would have a bottom for the region and a top for the region. If we have that, then we can also write it down as an iterated integral. Let's say the bottom is y equals g of x, and the top is y equals h of x. So for every given x, the limits of y are going to be from the bottom, which is g of x. So limits of y are from g of x to h of x. And of course, x ranges from a to b. So for every given x between a and b, the limits of y are from bottom to top, g of x to h of x. And this region is called a vertically simple region because it's bounded by two constants on the sides and two functions on top and bottom. A region is called horizontally simple if it is kind of the other way around, which means it is bounded by two constants on top and bottom and bounded by two functions on the sides. So here is an example. Let's say the two constants up at the bottom and on top are c and d, and the two functions on the left and right are x equals g of y and x equals h of y. For any fixed y, so any fixed y that you take that ranges between c and d, x goes from the left to the right. Left is g of y and right is h of y. And this region is called a horizontally simple region because we go along these horizontal segments. Okay, let's do a couple of examples on this. So we'll look at this region that is in the xy plane, bounded by x axis. So I will draw the region. So it's bounded by the x-axis, which is that horizontal axis, bounded by the line x equals 1, and also bounded by the curve y equals x squared. So this point is right here. So the region is exactly this region. Now we're going to have to look at this region and identify whether this is in fact a horizontally simple region or a vertically simple region. So how do we know if it is a horizontally simple region or a vertically simple region? Here is how we know. We look at the left side. The left side is a constant. We look at the right side. The right side is also a constant. So let me use different colors for this. So the left side is x equals 0. The right side is x equals 1. Now, bottom of this region is y equals 0. Top of this region is also a function. So top of this region is y equals x squared. So this is in fact a vertically simple region. Okay, so how do we write down the double integral that they gave us? Let's actually read the question. It says, find the volume of the solid that lies above this region R. So this is our region. And below this surface. So the surface is given by this. So below this and above that. So in fact, our solid looks like this. It's below this and it is above this. If I call this one X and Y, it is this one is the base. This is our base, and it is bounded above by this curve that we have. So it's somewhere around here. And the question is to find the volume. First of all, the volume is going to be double integral over the region of the height, which is x squared plus y squared dA. Next, we have to change this one to dx dy by using the fact that this is vertically simple. So vertically simple. So x squared plus y squared remains intact. For every given x, if you take some x here, we will have a limit for y. What is the smallest value of y? It's the bottom, which is 0. And what is the upper limit for y? It is x squared dy. Next, we have to see what are the limits of x. Well, x can go from 0 to 1, and that would be dx. Let's evaluate this. So this is going to be integral from 0 to 1. Integral with respect to y would be x squared y plus y cubed over 3. And this is y equals 0 to y equals x squared, and then dx. integral from 0 to 1. We'll plug in x squared for y. We get x to the power of 4th plus x to the power of 6 over 3 dx. And when you plug in 0, you just get 0. So let's integrate this. This would be x to the power of 5th over 5 plus x to the power of 7 over 21. And this one is from 0 to 1. When we plug in 0, we just get 0. When we plug in 1, we get 1/5 plus 1 over 21. Taking the common denominator, we get 105, and numerator would be 26. So this is the answer for this problem. Okay, so now I'm going to talk about one other solution to this problem, because if you look at this region, this is in fact also a horizontally simple region. So I will give you one more solution to this problem. So looking at the region is, I'm going to draw that again. The region is also a horizontally simple region. Why? Because if you look at the bottom of this, the bottom is a constant. The top is also a constant, the constant of y equals 1. And the bottom is y equals 0. What is the right side? The right side is x equals 1. And the left side is x equals, let me use a different color. The left side is x equals root y. So that means the region is bounded by the left and right. So you can say, well, if I fix some y, here, y ranges from 0 to 1, and x ranges from left to right. What is the left? The left is root y, and right is exactly 1. So double integral over r of x squared plus y squared dA is equal to, so for any given y, dx, the limits for x are from root y to 1. And dy, range for y would be from 0 to 1. Now we can integrate the same way, and we should get the same answer. So this is integral from 0 to 1. Now we have to integrate with respect to x. So this would be x cubed over 3 plus y squared x. And this one is x equals root y to x equals 1. And then we have to integrate with respect to y. So this is integral from 0 to 1. When we plug in 1, we get 1/3 plus y squared minus, when we plug in root y, we get y root y. So y to the 3/2 over 3 plus y squared times y to the 1/2, or minus rather, that is y to the 5/2 dy. Next, we're going to integrate. We get y over 3 plus y cubed over 3 minus, this would be y to the 5/2. So y to the 5/2 times 2/5, and then divided by 3. Minus y to the 7/2 divided by 7/2, which is times 2/7. And this is from y equals 0 to y equals 1. Of course, at y equals 0, everything is 0. At y equals 1, we get 1/3 plus 1/3 minus 2/15 minus 2/7. Let's take the common denominator to see what we get. 2/3 minus, so 7 times 15, that's 105. And then we get 14, and then plus 30. So taking the common denominator of these two, we get 105. So 3 times 35, that's 105. So we get 70 on top minus 44. And once we simplify that, we get what do we get? We get 26 over 105. And let's see if that's what we got. Yeah, so 26 over 105 is exactly what we got for the other, using the other method as well. Okay, let's do one more example on this one. Evaluate the integral, double integral over r of x dA, where r is the region in the xy plane bounded by the line y equals x plus 2. So the very first step is always to draw the diagram. We have y equals x plus 2, so the intercept is 2. So it's this line. Y equals x plus 2 and parabola y equals x squared. So we have this region. Now, if we look at this region, we do have constants on the sides, and the top and bottom are functions of x. So the bottom is y equals x squared, and the top is y equals x plus 2. So this one is a vertically simple region. And we have to find the intersections. So y equals x squared, y equals x plus 2. We'll find the intersections. So x squared equals x plus 2. X squared minus x minus 2 equals 0. We get x minus 2, x plus 1 equals 0. So that gives us x equals 2 and negative 1. So this point is negative 1, and this point is 2. So let's now that we figured it is in fact a vertically simple region, let's set up the integral. Okay, so we have x. So if you take a fixed x, then y values are between the parabola and the line. So x squared to x plus 2, those are the limits of y. And x values go from negative 1 to 2. Now we'll have to integrate with respect to y first, and then with respect to x, and then that would be our answer. So integral from negative 1 to 2, integral of this one with respect to y would be x times y from y equals x squared to y equals x plus 2 dx. So this is equal to negative 1 to 2. We'll plug in x plus 2. We get x times x plus 2 minus x times x squared, which is x cubed dx. So this is integral from negative 1 to 2, x squared plus 2x minus x cubed dx. Okay, so now we're going to use the fundamental theorem of calculus. We get x cubed over 3 plus x squared minus x to the fourth over 4 from negative 1 to 2. So that would give us 8 over 3 plus 4 minus 16 over 4, which is 4, minus, so if you plug in negative 1, we get negative 1/3 plus 1 minus 1/4. And this can be simplified. This is whatever that ends up being. One thing that is useful to know is that, and I will do examples on this one at a later point, because the examples here are going to be pretty simple and things that you already know how to evaluate them using other methods, but I will get back to this point later. Area of a region R is evaluated by the double integral of 1. Why? Because if the height is 1, then the volume is the same as the area. So we're going to use swapping the order of integration to evaluate this integral. So we want to evaluate the integral of, this is an iterated double integral, integral from 0 to pi over 2, integral from y to pi over 2 of sine of x squared dx dy. We are going to draw the region corresponding to this iterated double integral. And then we will use the fact that this region is both vertically simple and horizontally simple. So if you look at this region, x values are between y and pi over 2. So we're going to draw y equals x. So x value starts from y and ends at pi over 2. So this point is pi over 2. So these are the x values. X values start from y and end at pi over 2. And then y values start from 0 and end at pi over 2, which means it is limited by on top pi over 2 and at the bottom 0. So this is the region that we are trying to evaluate integral over. So if I call this region R, then the given integral from 0 to pi over 2 from y to pi over 2 sine of x squared dy d, or rather dx dy is equal to double integral over this region of sine of x squared dA. One thing that I forgot to mention is that if you try to evaluate this uh, iterated double integral, it is impossible. It is impossible to evaluate this sine of x squared, integrate sine of x squared, which is why we can't really use like usual techniques of integration, use substitution, integration by parts. None of those techniques are going to work for this particular problem. So instead, we are going to relate that to a double integral, use the fact that the region is both horizontally simple and vertically simple, and we're going to evaluate this integral. So as you see, this region that we drew, the triangle, is both horizontally simple because there is a right, there is a left function, and it's also a vertically simple region. So we can actually evaluate this one as a vertically simple region. So let's do that. We are going to use the fact that this region is a vertically simple region. So we're going to use sine of x squared. Now, in order to do vertically simple, for every given x, we'll have to see what is the bottom and what is the top. The bottom value for y is always 0, so that would be 0. And the top value is the top function. It's this function. So that's the top function, which is y equals x. So the bottom value is 0 and the top value is x. And then the right and left, the smallest value of x and the largest value of x are 0 to pi over 2. And this is dx. So next we're going to just go ahead and evaluate. Since we are doing dy, sine of x squared is in fact a constant, so we can take it out of the integration. So the integral from 0 to pi over 2 sine of x squared, which is a constant, and what is the integral of a constant? It is just y times that constant. And this one can be evaluated from 0 to x, but this is dy. So we have to substitute y by x and y by 0. We'll do that and we evaluate this. So 0 to pi over 2. If you evaluate this one at y equals x, we get sine of x squared times x. If you evaluate at 0, you just get 0. So we get this one. Now this is a simple chain rule. If you look at negative cosine of x squared, derivative of negative cosine of x squared is sine of x squared, because derivative of cosine is negative sine. But then we have to multiply by 2x. But there is no 2 here, so we'll have to divide that by 2. And then we have to evaluate this from 0 to pi over 2. Next, we're going to plug in the endpoints. So if you plug in pi over 2, we get negative cosine of pi over 2 squared divided by 2. And then plus, we're going to plug in 0 here. We get plus 1/2 because cosine of 0 is 1 divided by 2, so that's 1/2. So the answer to this would be 1/2 times 1 minus cosine of pi squared over 4. So that is our answer to this problem. To summarize, what we did was we defined a double integral that evaluates the volume of the solid that lies above the region R in the xy plane and below the surface z equals f of xy. Of course, this is only when f of xy is positive. If f of xy is partly positive, partly negative, you get positive volumes minus the portions below the xy plane. If you have a region that is vertically simple, then you can do the Fubini's theorem. So if it is bounded above by h of x and below by g of x, y equals g of x, then we can turn the double integral into integral from g of x to h of x of f of xy d of y, and then from a to b for x. Some of the iterated integrals can be also evaluated by swapping the order of integration. So I will see you in the next video.